I hate to have you. Oh, there you go. Go ahead.
It's yeah. I'm sorry.
Okay.
Somehow it suddenly started?
Yeah,
What did you do?
I did nothing.
Okay.
Just waiting for it. Okay, welcome. Good afternoon. Welcome to today's HAO Colloquium. Today our speaker will be Hannah Schunker from the University of Newcastle in Australia. And Hannah was awarded her doctorate from Monash University in 2007 under the supervision of Professor Paul Kelly and worked closely with Dr. Doug Brown. She then took up a postdoc position at the Max Planck Institute for Solar System Research in the Department of Solar and Stellar Interiors under the director, Professor Laurent Giesen, and progressed to staff research scientist. In 2020, she made the bold decision to swap Schnitzels for sunshine and accepted an appointment at the University of Newcastle in Australia, and is currently an Australian Research Council Future Fellow. Hannah's overarching science goal is to understand the solar dynamo and is best known for her research results using helioseismology to constrain the formation and evolution of sunspots and active regions. I think today Hannah's talk will be focused on the onset and evolution of Joyce law. So welcome, Hannah, and please go ahead.
Thank you, Shinhao, for this very formal introduction. I didn't realize that would be read out loud. I thought it would just be read by each person individually. And for full disclosure, I asked ChatGPT to write a humorous one, so that was not all fully there. So that's my background. But what I'll talk about today is a little project, a little experiment that a PhD student did, William, who is the first author there under my name, William Roland Batty, trying to understand the onset and evolution of Joyce law. So Joyce law is shown here with this sunspot group, where the leading side is closer to the equator than the following side of this active region. Here we can see it in the line of sight magnetic field at the surface of the sun. We see the active regions, not the same one as what I showed on the previous slide, but they occur in pairs of opposite polarities. And Joy's law is a statistical law. So not all active regions follow Joy's law, but on average, they do. The tilt angle increases with latitude. So active regions that are in higher latitudes are more tilted than those at lower latitude on average. And so this suggests that perhaps the Coriolis force has something to do with this, because this also varies with latitude. The thin flux tube theory, which was very successful in explaining the origins of active regions, where a thin flux tube lies at the base of the convection zone. It becomes perturbed and rises up towards the surface. And presumably when the apex pushes through the surface, you have your mostly east-west aligned opposite polarities. As the flux tube is rising, it's rising into less dense atmosphere of the sun, and material is flowing down the legs. On the left side, what you see here is height below the surface and sort of this longitude that has been unwrapped here. The color scale shows prograde flows, and at the apex, you see a retrograde flow, so in this direction, of about 100 meters per second. And you can ignore these lines for now. This part of the movie, actually, I'll go to the next frame where it freezes at the end. You see that the top of the tube has this tilt to it. So this could explain Joy's law very nicely. Oh, sorry, I should have said that Coriolis force is acting on these flows, these downflows in the tube, producing this tilt that we see here. Is that about right? Good. So just I've adapted this from a shorter talk. So just to give you a clear view of how an active region emerges, this is a bit jumpy. You see here the flux emerges a bipole of low flux and quite small and close together. And as more and more flux emerges onto the surface, it becomes these concentrated, well-recognized concentrated kind of blobs and forms sunspots, which are visible then in the intensity. So to capture the beginnings of the emergence process, we need to look at the magnetograms to capture that. In a separate study, or a few studies, by looking at the observations, by tracking the motion of the polarities as an active region emerges in the magnetic field, we get this plot on the right-hand side. With time, the polarities start off close together. So we have the following polarity and the leading polarity close together. And then we have the positions as they move in time. So they're moving away from each other, just like you saw in the movie. So this is on average for a few hundred active regions. So on average, if you look at the very beginning, they emerge east-west aligned, not with a tilt. Then this latitudinal, and then the tilt angle increases as a function of time throughout the emergence process. So Joy's law sets in during the emergence. And this sort of suggests that it might be a near surface effect. We also found that the latitudinal dependence is only in the north-south direction and not in the east-west separation. The east-west separation is only dependent on how much flux emerges. So very large active regions will have the center of the polarities further apart, whereas the smaller ones will be close together. You don't have small active regions with polarities far apart. So I'd like to understand, could it be that near surface flows, is it possible that they could generate Joy's law? We used the Muram code to numerically solve the MHD equations in the near surface of the sun. So we have a box that is 15 megameters deep and 96 by 96 megameters in horizontal space. And we added the effect of the Coriolis force in the F-plane approximation. So the F-plane approximation ignores all vertical flows, and we're just looking at the horizontal flows. We've added the Coriolis acceleration in the equations here that Muram solves. And we have this F describes the F-plane approximation we have used. We've chosen a latitude of 15 degrees, but this means nothing when you consider that we have set the rotation rate to be about 100 times the solar rotation rate. So this is so we can detect the signal. On the sun, the Coriolis force would be too weak, and so you have this statistical effect. We want to see it directly in this single simulation. So we apply this F-plane approximation with the rotation of about 100 times the sun. This part is just showing you what it looks like. So we've taken the surface velocities. We have filtered the surface flows, the horizontal flows, for spatial scales between 15 and 25 megameters. And we're saying this is sort of a supergranule in this simulation. They're large scale, but recall the depth of the box is only, 15 megameters. So we identify regions of strong divergence, and we've centered these and averaged them to make the average supergranule in this simulation. So this is with no rotation, and we see divergence, which is the white, and converging flows are the black, and the arrows show the direction of the flows. So this is an average supergranule for what we filter for in the simulations. Then if we do that for the simulation with rotation in it, we see this the vertical motion of the flows very clearly from the Coriolis effect acting on the horizontal flows. So we see that. So it's just to show you that it's there and we can observe it. It's strong enough to observe. You don't see anything this clean in the actual sun. Then we had to generate an active region. So we've placed a flux tube at 11 megameters below the surface. It has a flux of 10 to the 21 Maxwells, which is equivalent to a weak active region. We added this, actually, if we just put this flux tube in, it rises very quickly and we don't get an apex. So we had to change the density profile along the flux tube, where we made it less dense at the center and a little more dense at either side to get this apex to rise up towards the surface and get the opposite polarities. Then we placed this in an initial condition, which had been already relaxed without magnetic field in it and without rotation. So we have a background convective flow that we place this flux tube in, and then we let the simulation run. So this is the simulation without rotation. You see the flux rise up towards the surface and the line of sight magnetic field at the surface. Here you see the upflows and downflows at a cut beneath the surface, and you see the intensity, and you see that it forms a couple of, pores. Not a well-formed active region, but you do get the opposite polarities there and a little bit of darkening in the intensity. So that looks nice. Yeah, go ahead.
Do you think this density decrease in the flux tube to get it to rise is what's also happening on the sun? Or do you think this is just something to make the simulation work?
This is something to make the simulation work. Any input? So,
Well,
this is to get that apex. One of the things that we are imagining might be happening is that convection is bringing the flux tubes up. So it might not be this density decrease there. And in the thin flux tube, I think it's the magnetic buoyancy that's causing it to rise. So it's something we've had to do to get that to happen. And the way we've done it, it rises too fast. So this shows the flux at the surface as a function of time. And I'm just choosing 6 hours as the time when emergence is over, because that's basically when all the flux has appeared at the surface here after that. So the emergence occurs over 2 hours, which is quite quick. And we see that it forms this weak bipole structure. I'm just going to average over the surface maps through the emergence process, so over this time. And so you see the positive polarity on this side, the negative polarity on this side, and you see these enormous outflows, like they're quite large. So the flux tube is rising so fast that it's just pushing all the mass out of the way, and you just get these big flows coming up. So this is, I just want to highlight, this is in contradiction with observations. So we know our flux tube is rising too fast.
you can reduce it by just reducing the buoyancy, right? You can just put in less buoyancy and then.
So, and it's a trade-off with how much computational time we have. We're not limitless. We're quite limited. So we've gone with that. And this is the simulation with rotation in it.
Phil has a question.
Yeah, I was just wondering what the upper boundary conditions are on the velocities and the magnetic field.
So I think this is the magnetic field at the surface at the upper boundary, which is 1 megameter above the surface. The magnetic field has to be vertical. And I think it's an open boundary for the velocities. I would have to check that though.
Typically,
Okay.
it's half open.
Half open.
Outflows allowed, inflows suppressed.
Yes.
Yeah.
Did you hear that, Phil? It's
No,
half.
I didn't actually.
Half open, that outflows are allowed to go out, but inflows are not allowed to come in. At the top
Okay.
boundary.
Thanks.
Sure. Thank you for asking. So now we have the 100 times the solar rotation in there. So again, you see the opposite polarities, but you see immediately that there's a tilt to this. This is very clear. So just watch it. The polarities are not as pronounced in this simulation, in the intensity, but you still see some of them forming. So again, we see, so now the red curve is the one with the 100 times the solar rotation. It again emerges very quickly. The difference in flux here is not significant. If we have a 10 to the 21 flux tube and it rises, we expect about 2 times 10 to the 21. So if there's 2 or 2.5, I don't see this difference as significant. They're about the same, but they rise too quickly. So if we average now over the emergence process here, we see again the opposite polarities, positive, negative, and you see these vortical flows from the enormous outflows that the emergence brings with it. So we have that. So this is what we have. So to understand how this is generated, we've taken the sort of traditional way that you might measure Joy's law on the sun and look at the flux-weighted location of each magnetic polarity in the simulation. So this shows as a function of time, the location of each polarity with looking at the flux weighting. So in this example, maybe by eye, you would pick the center to be here, but because you've got a bunch of black field, negative field here, it's kind of pulled a bit in this direction, but that's kind of typical to what you would do on the observations. So in this way, we can measure the tilt angle. And of course here, if we do the same thing, we see that it emerges tilted and this tilt continues. It doesn't change much.
Emerge tilted already?
Yeah. Go ahead.
What is the beginning you define? I mean, as soon as it appears, it's already tilted.
As soon as we have measurable flux, I would say at the surface where we can measure this, it's tilted.
So it's done during that little rise, that little, how many megameters? The depth of the.
It's at 11 megameters. So somewhere between 11 and the surface, it's done.
Okay.
It's there and it stays there. That was 0, that was 100. You see the tilt angle. And this is what I'm calling the geometric tilt angle. So this is how you would do it if you just observed this on the sun. You would measure the tilt angle, and I'm calling this geometric tilt angle. And we can plot these as a function of time. So for no rotation, we have the blue curve, and we see that it gets a sort of, what is this, minus 8 degrees or something tilt angle. So this gives us some estimation of the noise we have in the tilt angle, because this is basically from, there's no rotation in it. So this is from the buffeting from the convection. So you get a tilt angle from that. It's an estimate of the noise there. The simulation with 100 times the solar rotation emerges with about 30 degrees, maybe 30, and then increases to maybe 35. But again, it's within the uncertainties, but it is highly tilted. So the tilt changes a small amount in this time.
The observations back that up. Like if you look at the tilt with time since emergence, do the activations get more tilted or not?
Yes. So with the observations, on average, they start off east-west aligned and the tilt sets in.
Okay.
So this is not like observations. We're way off. But we can, yeah, maybe we're way off. Do you remember Robert's talk from 2 weeks ago?
Yeah, that's kind of why I was asking, because I thought he said the opposite.
Okay.
Yeah.
My apologies. There should be about 10 slides in here introducing this, but if you have a good recollection of Robert's talk, this is the Cartesian version of his equations from the reduction of the induction equation. So he goes through a bunch of steps there and ends up with this equation. I refer you to his talk or his paper or whatever. So this is the geometric. G is geometric position or separation of the polarity. And it's got 2 components to it. One is the horizontal flows, which is what we're looking at with the radial field. for the vertical field. And this is everything I've shown you. The other term is as the horizontal flux is pushed across the surface. So you've got vertical flows pushing horizontal flux across. So this is just for X, and you can write the same for Y. And I've just taken this over the other side of the equations to isolate this. So this is our geometric separation, which we have measured. So I'm calling this the flow component because we're looking at horizontal flows. I know there are vertical flows, but just don't worry about that for now. So this is the flow component of the X and the Y. So our question was, could the near surface flows generate this tilt angle? So I'm going to compute this term and see if it equals this term here. That's it.
Which equals which?
Sorry, let me come back, mouse. If the flows, the position
Equal to the left.
equals to what we measure geometrically. So I'm just rewriting this now. This is the flow component, and here's the equation for that. So we can go ahead and compute it. And we end up with the locations given by the spots. So they're not wildly different, but they tend to be closer together. So the position's not quite the same. And the same for the simulation with rotation. Fine. So the flows can apparently account for part of the polarity motion. On the right, what you're looking at is a function of time for the separation between the polarities in the north-south and east-west direction. This is measured in the traditional geometric way for the simulation without rotation, and the red is the simulation with rotation. And you can see that there is an offset between the geometric and the flows. So exactly like you saw in the maps, they're not quite making it out to where we're measuring it geometrically.
And this displacement, I assume you kind of would expect to decrease with latitude, the amount of displacement between these two.
I would expect them to increase with latitude, but there's no latitude in this plot.
I was just trying to think of a way how to look at observations and say if how much, you could look at observations and compare it to this. So if you look at these small flux emergence regions or whatever further away, what would you expect the displacement to be if it was attributed to this flow?
Right. So then I would do the same experiment on the sun, for example, but horizontal, and seeing if that's accounted for there. So here we have a gap. It can't fully account for it. The next plot I'm going to show you is just this curve minus this curve. And I'm calling this the remaining component. It's the geometric minus the flows. That's it. I'm just taking the difference between the dashed and the solid curves. So this here is the remaining. This shows me how much is not accounted for by the flows. Now, if we go back to Robert's equations, there was another term in there. So we looked at, this is the flows. This is the geometric measurement that we just make looking at the magnetic field. And then there is this component that is pushing the horizontal field across the surface. So that should be equivalent to this remaining component if it's all derived from the induction equation. And that is shown here by these dotted curves, which you see are not. They also have the opposite sign to this, to the difference between these two. So the difference between here and here is an open question that we don't fully understand. Could it be diffusion in the code that is not ideal, and it's somehow causing the magnetic field to move in the same direction and faster than the flows of where that's why the geometric measurement is further apart than the flows, perhaps. So that was looking at the separations. because we're going after Joy's law, I'm not entirely sure whether we even care. So we calculate the tilt angle by the regular arctan of the separation in the y direction and the x direction to get the tilt angle. And so here we have tilt angle as a function of time. This dash curve just shows when the flux emergence process is over, all the fluxes at the surface. Come back. So we see again the geometric curve in solid and the flow, the tilt angle from the flows in the dashed curve. It's a little less, maybe 5 degrees, but again, this simulation here gives you an estimate of the noise in that. So it's about the same. I'm not convinced this is significant. Now there's many different choices you could make when you measure the geometric angle. Perhaps you choose a threshold, and this puts it more on the pores that are formed. And so we tested a few of these, and just for demonstration purpose, we have the shaded curve in the background where we've chosen a threshold of 800 Gauss to compute the flux weighted location. And it doesn't change wildly. So we don't think it's a parameter in the method we've chosen to measure the tilt angle. So they're roughly equivalent. We think that the flows could potentially cause Joy's law in the near surface. But we did this for something that's scaled up wildly from the sun. So we're going to scale it back down and see if it seems feasible. So the rotation in the sun is 100 times less. The surface velocities that we see at the surface are 70 meters per second compared to what this simulation produces of 2 kilometers per second. And the emergence time on average takes 2 days compared to the 2 hours of the simulation. So the north-south separation should be given by the Coriolis force acting on the flows over some time. So we scale the north-south separation back down to the sun. And instead of 35 degrees, we get a value of 7 or 8 degrees, which is much more on the order of Joy's law on the sun. So we've scaled our experiment up and we can scale it back. So what I would like to, in the future, it would be nice to form well-structured or stronger active regions. But what we've simulated is similar to the beginning of an emergence. All active regions begin as weak bipolar fields, and that's what we've simulated here. But we would like to explore higher flux, more structured active regions, and that rise much more slowly. Perhaps Joy's law, how does Joy's law look in global simulations of these, what I'm calling passive flux tubes that are formed by the convection and pushed up by the convection rather than the magnetic field itself, and looking at the observational analysis of the flows. So that exactly like your question, Asha is sitting at the back of the room here, and this is part of her PhD project, is to quantify the onset of Joy's law, as a function of latitude. So to look at this and see if it's feasible that the east-west flows at the surface of the sun can produce this north-south motion, and see if we can see that as a function of latitude. That would be really convincing. So thank you for your time. Thank you for logging on. Thank you for listening. It's lovely to be here.
I think we have a question.
I should also say that this paper is no longer in prep. As of 2 days ago, it was submitted. So referees, get ready.
That's a question.
I think it's rather a comment.
Oh, HAO keeps the front door closed, locked. Okay.
Yeah. Oh, yeah. That was from before. Yeah.
Do you have other questions from the audience for Hannah?
I should have asked this Robert camera because at the moment I didn't think about this, but no, I think there could be another. Okay, so you're measuring the second term. If you can bring that equation back up, those two terms that measure the geometric separation, there are two contributions, those two. Okay, here in the simulation, you know it is truly Vx, it's the horizontal theta motion, you know. But observation, you're not, you're tracing apparent motion. So it's the apparent north-south drift. So it could be it's you know, in extreme case, it's a tilted field, tilted loop, just rising, and then you're seeing the deeper part.
Right. So that could be the
So
not to confuse with what I've said here geometrically, but that could be just a geometric
Right.
effect.
right, because observation, you couldn't tell whether it is truly a horizontal motion or rather it was just the thing, the deeper part approaching the surface.
So is that because so very basically I'd expect if it's just a flux tube and pretending it's static, it's not changing as it's coming through, right?
That's the
It just
extreme,
rises
yeah.
through like this,
Yeah.
then the tilt angle would be the same.
Uh-huh.
Like it would just continue the same way like we see in these simulations, because it just continues. But what we see and what makes it convincing for me observationally is that the east-west is flux dependent, but this north-south is latitudinally dependent, the north-south separation. So it's not just going like this. There's separate dependencies for the two components. This
Okay.
is interesting to me. But it could be that is the argument that we're looking at these teeny tiny little things. The flux tube is coming up towards the surface and the convection is picking up the flux and bringing up these teeny tiny little things that we're saying are, you know, the emergence beginning, but really it's not that important. And they're being buffeted by the convection. And then once there's enough flux, maybe our definition of emergence time is not appropriate, but I don't know how to determine that yet.
Right. Is there any way you can helium seismology determine the actual velocity to calculate the second component?
Vertical velocity?
No. The second part is the horizontal velocity. Is there any
Yeah.
way of really truly measure that plasma velocity? Oh,
So with
if you could,
we can absolutely measure the surface.
It's so true.
This is all of the surface, and we can definitely do the surface flows with helioseismology or LCT or
yeah, LCT is the
Sure,
same.
yeah,
LCT,
yeah.
you can
they correlate,
yeah, you're just
Wow.
tracking the apparent magnetic field.
or LCT of the granules. You could also do that.
Okay,
magnetic
then it's
field
plasma.
and look at the plasma.
Yeah, okay, I think, yeah, that mentioned, okay, there's a limit on how sensitive this horizontal velocity can measure with seismology, I guess.
Yes.
This is like meters. The velocity, right? It's too small.
It's meters per second in the sun.
Right.
Here it's kilometers per second. But
No, I mean, yeah, because I mean, the true observation part, it's very small.
yes,
Okay, thank you.
thank you.
I think we have two questions from online. Bill?
Yeah, thanks very much, Hannah. I don't know if we've ever met, but anyway, it's nice to meet you online and to hear about a nice numerical experiment. There's a couple of points that I'd like you to respond to, and I'm going to ask a couple of dumb questions because there was things I didn't understand. So, in scaling from 100 times the solar rotation rate, the Coriolis forces are going to be enormous throughout the convection zone, not just in the upper layer. So I would imagine that the experiment you're doing, I'm just wondering whether it can be actually scaled at all, because I would have thought that by the time a flux tube crosses the part of the convection zone that you haven't calculated, that the tilts would be so strong that it would be essentially random. And then the other thing that struck me was you're operating in a fairly small Reynolds number regime, and I would have thought that if you're rising too fast, that what is it else? What else? Because you've got convection eddies in there and you've got some dissipation. So what else can slow the rapid rise of this down?
So,
something
okay.
seems missing to me. I'm not sure what.
So to make the flux tube rise, we've had to change the density. And we could probably, I mean, we've done that completely artificially to get this apex to rise. And just the way we've done it, it is rising too fast. So that density perturbation should be smaller so that it rises more slowly. But with it rising more slowly, it will take longer to compute when it reaches the surface and the emergence process. So yes, if we had more time, I would really like to go back and look at that more carefully. Does that help with the
So
rise speed
I
loss?
guess the second question I had was really, is there some kind of contradiction here, a conundrum of some kind that, or are you really just doing a numerical experiment under conditions that you think are very, very interesting dynamically, but not perhaps as relevant to the sun as they might be?
Maybe.
Yeah. And
So
I mean, I think you only focus on the top layer, so you can do the experiment. If you would have the rest of the convection zone, it might become problematic
with the high rotation rate,
with the high rotation.
yes.
But I mean, then you anyway get into the regime of we don't understand the deep convection anyways, and it looks like there might be scales much larger than supergranulation. So
okay.
maybe the deep layers are anyway very different than we think they are. So I think the safest we can do these days is just focus on the top layers, because we do have a good handle on those, but deeper than 20 megameters, all hell breaks loose.
So one of the reasons we chose the horizontal flux tube rather than pushing something through the bottom, though, is that I didn't want to I didn't want to force where the polarities would end up. I wanted to see that how that would evolve from a horizontal tube without putting conditions on what's coming from below, just what the convection would do itself, except that we had it rise too fast. So that was, I hope that explains a little bit the philosophy behind why we chose that and the perturbations we had to put in.
It's a curious thing that you're doing, and the stuff that you have a lower and upper boundary condition, and that lower boundary condition is sort of what Matthias was addressing a little bit, is what on earth is going to arrive underneath this thing for a star rotating 100 times that of the sun. And so it just seemed a little, I just wanted to get a better understanding of what you thought this experiment was showing. And it really, I don't know, maybe I'm being pedantic, but I love the word experiment instead of simulation. Yeah, a simulation is something, I think, that's intended to compare more or less directly with observation. And I don't think we're really quite ready for that at this point. Although and I'm going to finish talking a moment.
Agreed.
What I thought was great was I saw a Facebook post today where somebody's managed to achieve some quantum computing breakthrough in doing in a few hours billions of normal calculations. So with the advent of quantum computing, you might get what you asked for.
Oh, then I wouldn't stop here. We just do the whole sun and be done with it, right? Like,
yeah. And,
what am I doing?
but I mean, it's that just happened yesterday. Facebook, we all know, is incredibly reliable and factual. So no, I mean, it's just a hint that something may interesting be actually happening right now in computational physics. So anyway, thank you so much once again.
No, thank you very much for your interest and your questions.
Thank you very much for nice introduction of your work and a very good overview. I have two questions, actually. Once you have this actually screwing of the magnetic field lines, how about the rate of change in magnetic helicity? Have you?
Great question. So the flux tube that we impose has no twist in it. So that's, and we looked briefly at the helicity at the surface, and it's not obviously dominated by helicity. It's in one direction or the other. But we haven't looked at this in detail, and we haven't looked a lot at what's happening below the surface on the way. So it definitely, you have that rise, but the twist of the magnetic field is not, of the flux tube is not there at the beginning. And I don't expect that anything would have generated a significant twist on the way up. Is that?
Okay, and then the second question, once you have this twist of the magnetic field and deformation, the magnetic tension force can be created somehow there. So maybe the Coriolis force and this kind of force can compete between each other somehow, or not?
Definitely. You'll have the magnetic tension, and I guess this has something to do with keeping it together or keeping the magnetic components where they are, the polarities where they are.
Mhm.
So it may not, that's right, it may not just be flows.
Thank you very much.
Do we have any more questions? If not, let's thank our speaker again.
Thank you for having me.
We'll see you tomorrow.
Oh yeah, for the next one.
This is a general question about Joyce law. I know people were trying to figure out for small scale emergent magnetic flux, but they also follow Joyce law. Do you know if people figured that out?